Scroll through social media today, and you will inevitably see someone wearing a glowing neon red consumer therapy mask. The aggressive marketing campaigns promise a miracle cure for everything, from wrinkles to fatigue, inviting a healthy dose of skepticism. Yet, beneath the modern hype sits a verified medical pedigree. In 1903, physician Niels Ryberg Finsen won the Nobel Prize in Physiology or Medicine for successfully treating skin tuberculosis with concentrated light. For decades, bright light therapy operated as a standard clinical tool in hospitals, treating infections and skin conditions long before the widespread use of antibiotics. The science saw an accidental resurgence in the 1990s. NASA scientists were using red light-emitting diodes, or LEDs, to experiment with growing plants in space. During the trials, they noticed that small cuts on their own hands were healing unusually quickly under the glow of the panels. This chart shows the rapid divergence between clinical trials and commercial interest. While peer-reviewed studies maintain a slow, steady climb, the consumer market is on an exponential curve. It is projected to surpass $1 billion by 2030, driven by wild, unregulated claims that the light can treat everything from aging skin to ADHD. ADHD, or Attention Deficit Hyperactivity Disorder, is a neurodevelopmental condition affecting focus and impulse control. Strip away the viral trends, however, and you find a legitimate biological mechanism. Researchers are mapping exactly how specific wavelengths interact with human tissue, and they are doing it at the cellular level. The fundamental question driving this research is mechanical. How does shining a colored bulb on the skin physically alter tissue and accelerate healing deep inside the body? The answer lies in photobiomodulation. Photobiomodulation is the clinical use of specific light wavelengths to influence internal cellular processes. This diagram illustrates how different wavelengths interact with human tissue. Shorter ultraviolet and blue waves scatter almost immediately at the surface. Red and near-infrared light, however, possess the physical property to bypass that surface scatter, passing through clothing and penetrating several centimeters deep. Those deep penetrating waves eventually reach a specific target, the mitochondria. Mitochondria are the organelles that act as the primary power plants inside most human cells. This schematic demonstrates the electron transport chain inside the mitochondria. As the red and near-infrared light hits cytochrome C oxidase, a key enzyme that helps convert nutrients into energy, the chain's movement physically accelerates. This activation triggers a massive boost in the production of adenosine triphosphate, or ATP. ATP is the primary molecular fuel that provides energy for cellular functions. With a surplus of ATP, the surrounding tissue experiences immediate downstream effects. Local blood flow improves, and the cell exhibits a measurable reduction in oxidative stress and inflammation. The light is a physical catalyst. It provides the exact energy required to kickstart the body's own mechanical repair system. Researchers are now tracking these effects far beyond localized skin repair. They are finding measurable results deep within the brain and across severe systemic diseases. In early trials for Parkinson's disease, scientists are threading optical fibers directly into deep brain tissue to deliver near-infrared light. They are attempting to actively preserve the specific neurons that produce dopamine, the critical chemical messenger whose loss drives the disorder's progression. Evidence also suggests that mitochondria communicate with one another, functioning as an interconnected community across the entire human body. Look at this line graph comparing post-meal blood sugar curves. In one study, applying red light to a subject's back for just 15 minutes resulted in a noticeably flattened blood sugar curve compared to the standard steep spike of the control group. Photobiomodulation is evolving from a localized treatment into a systemic therapy, one capable of shifting global metabolic and neurological health. There is, however, a strict biological condition for this therapy to work. The metabolic state of the cell dictates the response. When near-infrared light hits a perfectly healthy cell, little happens. But when it hits a cell suffering metabolic stress, its energy output rapidly increases. This creates a biological sweet spot for dosage. Too few photons have no effect, and an overdose negates clinical benefits. Hitting that narrow peak requires exact wavelengths and high-intensity output. You find this precision in clinical-grade medical panels, not in the random, unregulated dosages provided by over-the-counter consumer masks. Treating photobiomodulation as a generic wellness trend strips it of its power. True biological recovery requires precise, targeted science.